All right, hi everybody. Hope you're all doing well and welcome to the second lecture of the first module. It's about definitions, so it can be pretty boring. So I'll just say that up front, and you should probably get a notebook so you can take some notes to stay awake, maybe a cup of coffee or something. Anyway, I'll try to keep it relevant with some good examples, but it's a little bit dry. The book also has all these definitions and more good examples, so if you want any more information, I really recommend Chapter 2. So the sensors we're going to look at for examples are three that I've used in drone autopilots before. They're all fairly old sensors, going back about 20 years. The MPX 4115A is a pressure sensor used to measure altitude. It can measure pressure from atmospheric changes. So you could use it as a barometer too. I think it was designed for fuel injection adjustments on cars. Also a rate gyro made by Analog Devices, the ADX-RS150 and the ADXL320 accelerometer. So a rate gyro measures how fast you're turning. It doesn't measure angle, but turn rate in degrees per second. Accelerometers measure acceleration in Gs. They also measure acceleration from gravity, so at least coupled into that measurement as well. So just to see some of the specifications here, we're going to be looking at the data sheets. You can get the whole data sheet on Brightspace if you want to take a look. That's a good thing to do too. I'll just be showing you cuts from the data sheets. That's where all of these images come from. All right, so the first two definitions are range and span. Range is, you have to know the range before you buy a sensor, so I say it's of primary importance because it's the maximum and the minimum that you can measure. So it's two numbers to give the range. And if you are trying to measure something outside the range, the sensor won't work. So it's right there at the top of most data sheets. Along with the range, sometimes you'll hear people talk about the span, which is the maximum minus the minimum. So a single number gives the span. So looking at the pressure sensor, the MPX 4115A, it has the range right here, 15 to 115 kilopascals, or 2.2 to 16.7 psi. Atmospheric pressures in the 14s or 15 psi range, so that's what it's designed to measure. The yaw rate gyro, the ADX-RS150, right up here at the top, 150 degrees per second, plus or minus 150 degrees per second. So the span would be 300 degrees per second. And the accelerometer right here, plus or minus 5 Gs. It's also in other tables that we'll see later. But it's so important they put it right up here at the top, because if you need to measure 10 Gs, this isn't going to work. So sensitivity is another one that is of primary importance, I'm going to say. Because you can't use a sensor unless you know its sensitivity. So sensitivity has to do with the output of the sensor, which is usually electrical, volts or something like that. And the sensitivity is how much the output changes for a given change in the input, the thing you're measuring. So it's a ratio. It's the change in sensor output divided by the change in sensor input. It's like, you can also think of it as a slope of a curve. And the units of this are critical, because if this is in millivolts, the output, that's 1,000 times smaller than if it's in volts. So you really have to know the units of the sensitivity, or else that number is just worthless. There isn't a standard. You have to always give the units. So looking at our examples, this is the pressure sensor. You can see, well, here is the sensitivity, 45.9. This is the typical column. there's a minimum and the maximum for some of the other parameters. 45.9 millivolts per kilopascal. So if you change 1 kilopascal, you can expect it to change 45.9 millivolts. Other things to notice, this chip was originally designed as a Motorola product, which is where the M comes from. Motorola was sold to Freescale, who was sold, I think, to some other people, and they basically take the same datasheet and they just stamp their name, so it gets kind of messy in the edges as the companies get sold. All right, so sensitivity is what we're on. So here's the sensitivity for the gyro, 12.5 millivolts per degree per second. So degrees per second is how fast it's turning. So that's the input, and the output is in millivolts. So 12.5 is typical, and they give a range here. So if it's between 11.25 and 13.75, they will sell it. And if it's outside that range, they'll toss it or sell it as a cheaper part or something. And the accelerometer, the ADXL320, 174 millivolts per G. And again, there's a range here, which is why if you've ever flown like a little quadcopter drone, you always have to calibrate the accelerometers by turning it over and letting it sit for a minute, usually to calibrate these kinds of things. So the sensitivity is the slope if you make a plot of output versus input. That's what this graph is. This is from the pressure sensor, the altimeter chip. And so the slope is the sensitivity, change in output over change in input, rise over run. And the assumption on a lot of these is that if you have 0 input, you'll get 0 output, which makes sense for something like a gyro. 0 degrees per second is holding still, so you get 0 volts, and then it goes positive voltage and negative voltage around that. But other things don't. So the MPX 4115 has an offset. So you can see here at it hits 0 volts somewhere not at 0 kilopascals. So they provide this chart that's really useful. They want you to use their parts, so they provide good data. And there's actually just an equation here. So normally you would be solving for P, the pressure, given the voltage V out. This form is what you get from a calibration experiment where you know the pressure and you're measuring the V out. That's this calibration kind of plot. But normally in practice you would be solving for P given V out, and there's just a nice equation here. Again, the data sheet is where this comes from. So accuracy is something that we were really interested in, and we will be calculating for some of our experiments. It's how close the measurement is to the truth. It's an estimate of the error. And usually you see it in a percentage. And so whenever you see percentages, you have to think about what do they divide by to get a percentage, because if you divide by a big number, you get a smaller percentage. So sometimes there's a little marketing involved. So the general practice is to divide by the full scale or the span. So it's the percentage of the span that you'll see in a lot of these. But you'll see if you dig through actual data sheets, it's hard to pin companies down on accuracy. They don't always give you a single number. So Analog Devices, who makes both the accelerometer and gyro, they have just paragraphs of things that change accuracy without a lot of detail, where they won't give you a single number. So typically less than 3 millig's over the -20 Celsius to +20 Celsius. So they give you estimates of different parts of the error, but they won't sum it up in 10% or something like that. That's too vague, I think. So they're a little more specific. If we look at the pressure sensor, they do give plus or minus 1.5% of VFSS. sounds like a full scale FS kind of a thing. So they do give you a number, and then there's a big footnote 5, so I cut out footnote 5, and so accuracy is due to all of these things combined together to give you their worst case estimate. So plus or minus 1.5%, and you can see VFSS is here, it's on this column above it, so VFSS, typically 4.59 volts. So you can dig around, and there's a footnote explaining what that means too. You'll have to look at the data sheet for that one. All right, so just an example of using the numbers. So this would be a good one to copy down and follow along with. Given the accuracy of 1.5% of the full scale span voltage, what is that in kilopascals, or what is that in feet of altitude? And we use this for an altimeter. So we have VFSS as 4.59 volts typically. So we can change plus or minus 1.5% of that voltage to a voltage here. So plus or minus 0.06885 volts, multiplying these two together. And then to get that to kilopascals, the pressure change, we use the sensitivity. So sensitivity is really a unit changer or a slope. So it's 45.9 millivolts per kilopascal. So we can use it to change volts into kilopascals. So if we take plus or minus 0.06885 volts, divide it by 0.0459 volts, which is 45.9 millivolts per kilopascal, then the volts over the volts cancels out, and we get a 1 over kilopascals. So we end up with plus or minus 1.5 kilopascals. Doesn't seem right. Oh, maybe it is. Because it started with 1.5. Anyway, I did the math. I think it's okay. Yeah, so that's how you can change the units using the sensitivity. So you're going to get outputs in voltage, and you're going to need to know kilopascals, and so the sensitivity is what you use for that. All right, so there are a lot of other definitions in Chapter 2, and we're only going to go through not all of them. I pared this down over the years to the ones that we use the most in the class. You'll see some other ones. One thing to pay attention to is that these words have exact meanings in our textbook, but in general usage, they are somewhat interchangeable. So people talk about precision or accuracy or resolution. They might just be talking about how good a sensor is, but here we have specific meanings. Accuracy is related to the error, the comparison to the truth. Precision here is how repeatable or not random something is. So if the same thing happens over and over again, even if it's bad, it's precise. So it's different from accuracy. Resolution is the smallest change that can be measured. So think about the digits on your voltmeter. Drift is something changing generally slowly over time. Thermal stability, drift due to temperature changes. Linearity, we like linear calibration plots, and so if it's not, we can give that as a percentage. And hysteresis is something that is related to whether you're increasing or decreasing the measurements, and how does that change a future measurement. So the history is involved in hysteresis. So let's look at some examples of these. And again, if you look in the textbook, there is more detail. Linearity. Here is the diagram from the book on explaining linearity. And again, we've got the input to the sensor, the thing that we're measuring on the x-axis, and the output of the sensor on the y-axis. So it's a calibration plot. And normally we would just fit a straight line to the data that we've got. And so that's what this dashed line is showing. Straight line and a different straight line here for the ideal measuring device. And the actual data is this curve, and so we can find the biggest difference between the linear line and the actual and call that the error. So in the beginning here, we're going to just look for the worst case and call that a linearity error, but that's what they're talking about when we talk about linearity. It's like we would like all the data to lie on a line, but it doesn't. Hysteresis is something that happens when you're, again, here we've got the thing we're measuring on the x-axis and the output of the sensor on the y-axis. And we have the plots, the calibration plot. And if there's hysteresis in your system, when you go from a low value, a small value of your measure end to a large value, as it increases, you get one path. And then if you go from big back to small, you get a different path. And so the reading that you get depends on if the one before it was bigger or smaller. If you're going from here to here, or if you're going from here to here, you get a different number. And if that's due to the motion, the history, then you get hysteresis. This is common, especially in things like mechanical systems. So if you imagine a mechanical spring scale that goes up and down with the weight putting on it, there's friction in that motion. And so that if the weight is going down, if you're getting heavier and heavier, the friction pushes up. And so you'll tend to weigh off in one direction. But then if you're going from a heavy weight to a lighter weight, the friction's pushing down, and so it tends to weigh a little bit heavy. So friction in a mechanical spring is one kind of hysteresis, and there are other ways to get it into a system as well. So when you do the calibration, you generally are careful about measuring it when you're increasing and measuring it when you're decreasing. Then you can compare the two and see if there is any hysteresis. If they're the same, then there isn't. All right, so the last example here is some data that I took with a drone airplane that I used to have. I wrote a lot of software for it, so I had one in my shop for a long time. So this was about a 6-foot wingspan, gas-powered drone, and I worked on the software and some of the autopilot stuff. So I turned it on and I let it log data on its data recorder for a few minutes. So here's time on the x-axis. And then the output of this sensor, the MPX4115A that was in this autopilot, is plotted on the y-axis in kilopascals. So I changed it from volts to kilopascals using the sensitivity. We would actually change this to altitude in feet or meters using a standard atmosphere table. So there's an equation for the standard pressure at different altitudes. So that would be our starting point. So the altitude's not changing. The plane is sitting still, and you can see that the measurements change. We've got a ton of measurements because it's easy to do with the computer. And so the question is, what is the altitude? So what would you do with all of this data? So generally, if you know it's not moving, you could just average it. So the average is the red line here. It goes right through the middle of everything. And if there's some steady offset, a bias, then the true might be up here. And so there's the randomness that you see from the noise here, and there's also some drift. So there are at least two sources of error, the random error here and the drift that are giving us our average. So if we let this sit on the bench and it kept drifting this way, our average would also change over time. And so these are just some of the problems you have to solve. This altimeter was pretty known to drift. It drifted mostly with temperature. So as the electronics warmed up, or if you flew the plane really high where it was cooler up high, you would have altitude change, but it wasn't enough the plane flew fine. The plane was 10 feet higher than it thought it was. That was close enough for the kind of work that we did. And we would always have it grab the pressure on the ground as the 0 altitude, to use that for landing. So the worst thing that would happen is if you flew for an hour, sometimes you would get 10 feet of drift in the altitude, and it would overshoot or undershoot the landing because the glide slope was fairly shallow. So that was the only problem we had with this altimeter, and it worked really well otherwise. So we just went with it and had long runways. You could do other things like radar and sonar and stuff, but we didn't need to. All right, so you have a bunch of data and you average it and hope that you've got good data. And so you test it out with calibration plots to make sure it's working. I think the last thing here is looking at resolution as one of the terms. Resolution is the smallest change that you can measure, and you can see it here by not connecting the measurements. These are really going up and down. If I go back one, oh, I can't. Anyway, these are all connected with these noisy lines, but you can see that when you go from here to here, it doesn't measure any change until it gets to here, and then it's locked in here. So these are the discrete bands of resolution of this particular system. And these can be from the sensor itself has a resolution. This was an analog sensor, so this was pretty coarse. So I think this is from the digitizing, the analog to digital conversion that goes into the flight computer. So things like if you have 3 digits on your multimeter, it rounds it off to the last digit. So that's what we're seeing here, the resolution. So we'll see analog to digital converters later in the class, and we'll talk about their resolution. If you needed to measure finer than this, I think this was a little less than a foot of resolution that we could detect changes in, and that was fine for this plane. But if you needed more, you'd have to build a different system. All right, I think that is everything. So hope you got something out of this lecture. Hope you took some notes. Don't forget to take the quiz afterwards, and email me if you've got any questions, or put them on the forum, or get in touch. Happy to help. Take care. Bye-bye.